Okay, so I'm working Schrodinger's equation here. Again, this is for the beginner's version of it, but basically I just wrote it down here and I broke it down for the worker's function the best I could. Here we're actually going to spell it out and say H in this case is Hubble's permanent. It is the constant of the expansion of the universe, essentially, the universe expansion. In this case, we're also going to say T is in the whole function here. Time at point past 0, 1. So from the fox and rabbit calc, like you're dealing with that kind of ratio, and that's why you'll see UV here, V equals 1 and V equals 2, because eventually we're going to get into this being some standard stuff later on. Alright, so then we got this integration of what I call the dimension, or the vector with the wave function in continuance to that timeline problem, because we're saying we're not worried about the one before the Big Bang. We're not saying that the distances of the temperature where the soup of the temperature was too much. We're saying past that into now this state of very fast at the Big Bang. And you'd see that by this is that negative aspect. It's a -1 past into +2 futures. So we're saying like this is that ratio on that, and that's integrated by the square root of -1, which is I, and then we're saying that that's a square root to determine some kind of offset angles and stuff. We'll get into that later. Hopefully just hang with me for right now. Now this is Planck's constant. This is that shortest distance, 0, 1, regardless of scale or what aspect you're dealing with there, because that becomes time. That becomes time at the Big Bang and at the constant rate that it's expanding. Now this is important for what I said here is coefficient of derivative and the coefficient of time. And in this case we said for 1, treads equal $11 a square foot, 3 foot plus. And 2 for this is $15 per hour x treads. And we're correlating that to say that in here, general value at point A is time. And we're integrating that to say that 8 footers treads is what we'll get in that time, and that correlates to 8 times $88, because that's how many pieces of the value, which correlates to what is it, $704 per hour, against new calculus form, because you would take that constant and you would say if that was the permanent constant to Hubble's constant, then it also becomes Planck's constant, and they adjust under those numbers within the wave function of that calculus here, negative or positive on those integrals of scale. See, if this number scales differently, it has some kind of redshifting value to it that an operation or a neutrino or something can affect in that way, then essentially what we're dealing with is the multi-world circumstances. And this also applies to additional faculties. That's to say, at 80, that doesn't sub out to all the pieces of that job when you square that root. Here the square root of -1 by rational values. I know that number doesn't make sense to what I do mechanically to the actions. Even if it does, there's 4 other people in there. So let's divide that $700 by 4. And you're supposed to get $200, 100 and something odd dollars, and you do that for, all right, so that's the hours, and then you got equipment, and you got all of these other spectrums that would say, well, somewhere's in there that value by ratio is how I'm working it down. See, I could say that value works, and we could use this math, and I could say from the stone mill at $1, you're actually making $1 a square foot. Do those ratios really work off? Because one's going to be Planck and one's going to be Hubble. They're going to adjust to each other from whatever territory or topography I had to help me narrow down on what number is left over, what's the cost left over, whether I'm negative on it or that's a positive debt that I have, so I have extra money in there to deal with timelines or how that reciprocals into those, because you get it from both sides. And that's again that wave function aspect. You're going to get into a lot of that while dealing with calculus or where its position is, -1s and +1s, because at the beginning it's very likely that you'll miss. Or even out here that something could crash that to a 0 state, or even put you in negative forms that then you would have to physics pass. And see, that would change the ratio of Hubble's or Planck's constant after the smallest distance is 0. So once you hit that 0 bar, you're basically saying that this is a company in debt. And in order to do that, the same rules of a company that's not in debt wouldn't operate. So we're not adding an additional X to it, or we're not saying that there's an additional term for that. Now, see, the function is different with some kind of sine or cosine, or the way time is behaving. There's some kind of adjustment, or how they position it in here. There's a trifecta or an x, y, z variable on it to an x, y, x, y, x, y. And here's one, there's one of them, two of them, no rational I, no h. I might have got this equation wrong. I think there's another h in here somewheres. As a matter of fact, I think it's up there. But at any rate, you can those things again. As soon as I change out this constant, let's use the lowercase h, or a h with a 0 on it. You know, whatever math equation you'll see, Hubble's constant, it's in a couple of different forms, and so I want to check off those other forms. I don't know how you've learned Schrodinger before. This is how I want to present the information to you. We're not going to break down just parentheses. Here, this is that action that says away from Hubble's constant, the constant expansion of the universe, time. That's how we dictate that. On Mars, time is different, and if you go back to the Big Bang, the way that time would work would also be constant to the value being 0 on that graph, 1 on that graph, or in some way to the rabbit and wolf calc, where it's not just one wolf and one rabbit, or one wolf and two rabbits. There, a timeline of the days wouldn't sequence. That way it would be some physics, some operating x, y, z function to that mechanics. And again, that's going to be coefficient of derivative and coefficient of time. I just got to name them both. They both become a constant in this equation at that field, and one's going to be a time value to Hubble, our expansion, and one's going to be a space value given Planck's 0 to 1. Catch you on the next one.